This video segment, I would like to show you how to do an elastic plastic analysis where the Johnson-Cook material model parameters are supplied to the uh, 3DEXPERIENCE native FEA solver. And this is in release 2022x. So in an earlier video, I did the same problem except that the information was supplied to the software in the form of uh, tables of true stress versus true strain uh, at different strain rates. The difference between that problem and this one is that the data that I took in the other video are fitted into the Johnson-Cook model and the parameters are fed into the software. Okay, so both the data and the parameters calculated are taken from this nice reference. Okay, one other reminder is that the purpose of these videos is to show novice users or some Abacus users how to uh, adjust from the Abacus interface to the 3DEXPERIENCE interface, because not everything is the same. Although the native solver of 3DEXPERIENCE is Abacus, but the icons are different, some functionalities are different, and therefore it's not should not be taken for granted that one can jump into 3DEXPERIENCE and do FEA with it, even though they may be experienced Abacus CAE user. It requires some detective work. Okay, so let me move on here. The Johnson-Cook parameters are these 8 numbers that have to be fed into this model, and the values that I'm taking from that reference for the parameters are here. Notice that there is no temperature effect in this problem, and therefore for the melting temperature and transition temperature you can take anything you want, except that these should not be the same, because if they're the same it's divided by 0. And when you exponent, you specify the exponent of thermal effect as 0. Basically, this really does not come into the picture at all. Okay. Now, the problem that we're going to do is this bar, which is going to be meshed with parabolic element, 10 of them, and there are 3 planes of symmetry, and this NEFGH is actually loaded with displaced by 2 millimeters in 5 seconds. Although the problem is going to be done statically, however, and this is not real time, the time is not real time, but it should be consistent. In other words, 2 millimeter over what period, okay? And that, so this should match with the strain rate that you're interested in. In other words, the strain is 2 over 50. This is 2 millimeter over 50 millimeter, and over 5-second dummy period is going to be strain rate of 0.008. Now this problem came from the one that's up here. Because of symmetry, we need to take only 1/8 of the model, and there are 3 planes of symmetry. And here's the table in 3DEXPERIENCE that you have to fill in. There are 8 parameters, as you can see. 5 of them are here, or 6 of them are here, and the other 2 is if you check this this rate dependent line here, branch here, these 2 are going to pop up, and altogether there's 8 of them. Okay, and there's a nice video description of how these parameters can be obtained, which is given there. Okay, so let's go ahead and do this. The model is a block. So on that vertical plane, I will sketch a 5 millimeter by 5 millimeter, a 5 millimeter by 5 millimeter square. So let's see now. This is going to be 5 mm, and this is also going to be 5 mm. And we exit, and we pad this thing by 50 millimeter. Let's see now, 50 millimeters. All right, now we're going to create our material information. So under tools, create a material, and I'm going to call it JC Johnson Cook April 23rd, 2022. Okay, All right, so let's see now. It's right here. Right click, apply. And we can close this, apply it to that part. Check mark closes that. And we go and input the data. Okay, so first of all, we're solving the problem as static, so density is not required here. Abacus multiphysics, mechanical, elasticity, elastic. The Young's modulus was 200,000 MPa. I've already changed my units to units of stress to MPa here, so 200,000. Poisson ratio is 0.37. Okay, and then we go to plasticity, metal plasticity, plastic, select the plastic and select the plastic, and then we don't want tabular. That's the one that was done in the previous video. Now we're going to do Johnson Cook. These are the first four parameters that we have to input. So this is 26. A was 26. This is 280. I believe this parameter n was 0.31. So this exponent is 0.31. M is 0, and these temperatures are not used. So, but I believe you have to supply them, or you, you can see if you left at 0, what happens. I'm not 100% sure. So let's see. I'm gonna make melting temperature of 500 degrees C. Oops, kick me out. Let's go back here. Plastic. Yeah, and then transition temperature. Uh, you can leave the transition temperature the same. Well, I'll make it 0C. 0C degree. Okay, good. Now, if you select the on the plastic, if you wait a minute. Yeah, if you select the plastic rate dependent, then it allows you to input the other two numbers. So change this thing to Johnson Cook, and your value of C is 0.07, and the epsilon 0 dot is 3 zeros and 7. So this one is 0.07, and this is 0.3 zeros and a 7. Got it? Yep. And we say OK. Now we're going to go on mesh it, structural model creation, standard. We're going to do, first of all, the selected geometry. Make sure you select the part. And then swept mesh, parabolic, 5 millimeter, and number of layer 1. Depending on how your model created, this should be 1 or 10. Let's see how this thing works. Update. Yeah, okay. In the other video that I did, I believe that the mesh was done in this direction, swept was done in this direction. That's why I had to put a one layer in this direction. Okay, well that's good. Let's hide this. Let me hide this. These elements. Now we're going to go to structural scenario creation. We use the mesh that was created. Okay. So as far as the procedure is concerned, it's a static analysis that we're doing. The time, although dummy, it should be reflecting the correct strain rate. So I'm going to put a 5 here, and the reason you can see why, because it says 2 millimeter over 5, although dummy, but 5 second is going to give you a strain rate of 0.008. So that's fine. Initial time 0.01, maximum time step of 1 second, and I will leave the geometric nonlinearity here, but that's, you should see what the effect is if this is not checked. Okay, basically, if there's large deformation, you have to leave this thing there. And I think in my case there is large deformation. Okay, now as far as the restraints are concerned, plane of symmetry, there is one here, there is one there. You have to do these separately, and there is one at the end. Okay, and we're going to apply a load. The load is actually translation, specified translation on this face in the direction y, magnitude of 2 millimeters, and that's pretty much it. Okay, so the one other thing that we want to do is when we go to simulate, we ask for extra data. I mean, the standard data is deformation, displacement, and things like that. We're going to ask for a few more things. We're going to ask for all component of stress, in case you want to plot something, and all components of a total strain and plastic strain. So total strain is elastic strain plus plastic strain. Yeah, good. So this is in case you want to get a contour of those things. The first thing that we're going to do is we model check. A very simple model. I don't think there's going to be any issues with it. Then we do a simulation check in case anything. For example, in the other video segment that I did this. It told me that there were no licenses available. So that's why, I had to go and do something. Okay. This one is going to go through, no problem. And then we're going to run it, which means simulate. There is a warning. It's a good idea to read these warnings. This, I'm sure, is not an issue. And finally, simulate. Remember, this Johnson-Cook model works for static, dynamic, and dynamic analysis. Therefore, although I'm doing it for static case here, but if you have a dynamic problem, implicit or explicit, you can still use a Johnson-Cook model, or, for example, give experimental stress strain data at different stress strain rates and different temperatures if needed. My problem, I'm ignoring the effect of temperature. But I'm sure if you had asked for temperature effect, there would have been another column probably where the temperatures are listed there. All right, it did run. Okay, so let me close this. Nothing exciting here, so it did it very quickly, as you can see. This is the initial increment. Everything is 0. Then as you increase the displacement or load, if you want, the von Mises test is going to go higher, 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 higher. But nothing exciting because this is a uniaxial problem. The restraints are, planes of symmetry. Therefore, basically everywhere you have the same von Mises stress. If you go to displacement, on the other hand, and if you go to the last step, for example, last increment, you should get 2 millimeters, and you will. What is the 2 millimeters? Right here, you can see that. And you can plot other things, which are, again, not very exciting. Plastic strain, all the same color. If you want safety or factor of safety, wait a minute, this is the last step. Everything is yielded, correct? Factor of safety, everything has yielded. Factor of safety is below 1. Everything is yielded. If you start at the beginning, not everything is yielded. I mean, actually, you can see that factor of safety is not yielded yet. So, but as you go further, this thing goes further down, and factor of safety falls below 1. That's pretty much it. Good luck.